So our lab 8 was actually analog to digital converter, and our task was to make a temperature sensor using Arduino. So I will show you the code over here. Assalamu alaikum, it's Anis180925. So over here, first of all, I have just initialized the libraries, okay, and declare a function of the car TOINT, okay. And now what I'm doing is actually in the main body of the loop I have just declared two ports as an output port, port D and B, and then I am initializing the LCD. Then I have declared a variable. Then I have made an array of the then the I have initialized a variable Q, then DDRC port C as an input port, and then I'm using analog to digital mux. Okay, it is used to set a channel. Okay, and I have selected a 5, okay, with an external capacitor at AFR pin, as you can see in the comments. Now over here, now ADCSRA is actually used to enable the ADC, analog to digital converter conversion interrupt, okay, on the clock of the 128 frequency. 28 hertz will be the frequency of the clock. After that, in the while function, actually what I am doing is just starting the conversion, because we have to display the temperature on the LCD screen. So in order to check that which value is being received, we are just doing some conversion to check that if the value is correct, and then we will display on the LCD. And now here is an end condition, okay, which will be waiting to check if our conversion is complete or not. And after that, we will just create that flag, and we will just move towards over here. Actually, we are just setting the ADC, analog to digital converter value, which is 9.3. After that, I am just assigning that value to the Q variable that I have declared, and then I am just displaying that data on the LCD. As you know, sir, you have to this switch case statement was written because our LCD was displaying some data which was not right. So it was displaying the numbers in the hexadecimal system, and now what we are doing is just right, we have write this function over where we have just write a bunch of numbers telling that if this number appears in hexa, you have to display this on the LCD. So I will just simulate it first to show you if it's working or not. So I have to go below 5. I don't know why it's not working right now, but it was working in the lab, and I did showed you over there. I don't know why my LCD is not displaying data right now. Maybe there is some problem, but well, just let's move to the next lab. But I did show you in the lab, but it was working properly at that time, so I will just check later what's wrong with it. So let's move towards the lab 9. So over here it is our lab 9. I will just open its Proteus first, and then move towards the code, and I will explain you there was only one task in the lab 9, and which was to blink an LEDs using PWM. I hope you do remember. Sorry about that. I am just having a little bit flu and cough and maybe a fever. So here is the code. I'm just including the interrupt library, input output library, and delay library. Then there is a duty cycle. Okay, and then there is a main body of the loop in which I have set the pin 6 of the port D as an high. Then I am just using the communication mode through which I will these register WGM WG00 in the register TCCR0. These are the bits which are used to set the communication mode, and TMASK is used to enable the register. Okay, now I'm just giving the duty cycle on which it will be operating, and this is the global variable for turning on the interrupts, and this is the register TCCR0B, which is used to set the clock frequency. If we are using a normal clock or pre-scaling or upper edge trigger or lower edge triggering, so after that there is a while which will keep on running forever. It will not let the program exit, and it will just keep on adding 10 in the duty cycle and check if the duty cycle is from greater than 100 or not. If it will be greater than 100, then it will set it to 0, because we have to turn on LED and then increase its brightness slowly. So this thing will be actually controlling the brightness and will keep on increasing the brightness of the LCD. And this is similarly we are just calling the timer, okay, interfunction. So here it is the Proteus simulations, and I will just move towards it, and after some time it will just start to turn on slowly. Fifth semester. Now you can see it is turned on as high. Now I will just pause the simulation, so you can see the brightness of the light decreasing. Look, the bright, now the light got dim and now it will be turned off. So as you can see, it turned off. Now it will turn on again. As you can see, after some delay, look, it got turned on, then it will got turned off again. So this is was our lab night. The control the brightness of the LCD using PWM. I hope you all understood it, and if there are some questions or queries, you can tell it to me and ask me. Now we will move towards our lab 10. Now our lab 10 was actually lab 10, 11, 12 were actually the labs that we do on FPGA and on the Cyclone. So I have the pictures of and the screenshots of the simulations of the quarters. This is the lab 10 pictures. Now there were actually 6 exercises in that lab. I simulated the code and then showed you, and I have the block diagram and everything. I will just show you from here. No, this was the block diagram of the exercise when that was made when we were using the code that you gave us in the handout, okay. And this was the input output waveforms, and this was the circuit built by the Quartus, okay, of the exercise 2 that was on the lab 10. And this was the input output, and this was the code that we simulated on it. Right now actually the Quartus is not working on my laptop. I don't know what's wrong, so I guess I'm just using screenshots and just telling you what we did. And this was the exercise 3 circuit diagram that was built after executing the code. And this was the waveform, okay, the input wave, and this was the code. As you can see over here, we just used a bitwise communication, okay. And this was the output waveform, and this was for the exercise 5. So now I will just show you the lab tasks 11 screenshots, okay. These are the lab task 11 screenshots. Over here we have to use the different methods and to use the quarters of the module, and you have explained us the code later, and which was very simple to check the control, how to control the bits using quarters or FPGAs. This was the circuit diagram built by the quarters of the lab 1. And sorry about that, this was the input and output wave, and this was the circuit diagram of the method 3 in which we have used a mux. And this is the code of the method 3, okay, that we executed on the quarters, and all the waveform and the circuit diagram was built and we just located it. And this is the waveform of the method 1, input waveform and output, and this is the code of the method 2, and this is the code of the method 1 that we simulated on the Quartus, and this was the circuit diagram of the method 2 that was built, and this is the waveform that was being built, input output waves of the method 2. Okay, so now let me tell you which method did we use. This was the handout. Okay, now FP in lab 3, first we perform the arithmetic operations using Quartus. As you can see, this is the code over here. What are we using? Actually just assigning a 3 and 0 to the two variables, and after that we have output variables c d e f g, and then a is equal to 12, b is equal to 3. Then we are just doing multiplication, storing that answer in the c, then the division answer in the variable d, addition answer in the e, f, subtraction answer in the variable f, and so on. Similarly, we use the logical gates to compare the values of the variable a and b using Quartet. Similarly, like that, we have used it in the other exercise. We use relational operators to check if our value is greater than or less than a or b or not. And we use the equality operators to check that if our bit in the binary, as you can see over here, we are just checking if our equality operators to check that whether our logical equality evaluates to 0 or not. Over here we are just checking it double equal will operate and check that if our equality is equal to 0 or not. Similarly, over here as you can read, then the next line is inequality to evaluates the x, then the logical inequality to evaluates the 1, and so on. Bitwise operator and the reduction operator to reduce the value one by one, and then the shift operator will be the shifting the values. And over here this is the exercise 6, and then we perform this lab number 11, which was using multiplexer mux, which have different type of method. Now the method of implementation were there were three. One was gate level implementation that I showed you first, and the block diagram, the code, and the input output wave, and the second method was the logical statement implementation that you can see over here. Okay, now after that what we do was the case statement implementation. Okay, and then we just simulate it on the quarters and the waveform were obtained. So now in lab 7 we perform task which was to follow the Verilog code using the 4-bit adder, and in the task 2 we use the unsigned 4-bit adder. And over here I have the screenshots. I'm really sorry, but the quarter is not working well, otherwise I would have performed it and showed it to you. But in lab I did show it to you because I was using the laptop of my groupmate, and right now the quarter is not quite working well. This is the waveform that was obtained by the 4-bit adder. Okay, and this is the input output where this is the circuit diagram that was built when we run the code that you gave to us on the quarters, and we located it. And then this is the waveform of the second task, and this was the 4-bit adder that we used by adding two adders in the and connected them. And that's all for now. Thank you so much for teaching us, and I hope you will you were the best.